Early Northwest Indians called this peak Comacoshan, White Steep Mountain. In 1792, Captain Vancouver named it Mount Baker after a lieutenant who sighted it from Puget Sound. Mount Baker is a volcanic peak which looms high above the North Cascade Mountains of western Washington. Its wide slopes bear a glistening mantle of active glaciers. These great fractured sheets of ice are slowly gouging out huge valleys down the southeast side. Though the effects of this carving process are enormous, the inexorable downward push could be recorded in mere feet per year. The resulting changes in Mount Baker's topography will not be apparent for generations. To study glaciation, volcanism, or any other process which shapes Mount Baker, one must examine remarkably diverse physical characteristics, many of which have developed over a span of time which makes a human lifetime seem like a mere instant. Mount Baker is not a static monolith of lava rock and ice. In this large crater basin now coming into view, there is dynamic interaction between the effects of geothermal energy from inside the mountain and the external effects of weather and erosion. The interplay of forces here has stirred much scientific interest. The sheer walls that surround most of the massive ice and snow in the crater basin open into a large gap on the far side formed by steep slopes covered with crumbling ice and hydrothermally altered rock. At the base of these slopes, in the deepest part of the crater, is an area of intense geothermal activity. Clouds of steamy sulfurous gases blast forth constantly from several large holes there called fumaroles. This shows the relative positions of the crater's major features: Pooch Peak and the west rim, which provides the easiest access; Sherman Crater, where the large ice mass lies; and Lahar Lookout, a promontory of unstable rock. Also, the East Gap area, where the largest, most active fumaroles have been, and Sherman Peak, one of the most strikingly beautiful features of the crater area. The summit of Mount Baker is Grant Peak, 10,778 feet high. Intense heating from below has melted a large pit out of the crater ice, and a lake has formed at the bottom of it. Fumarolic activity tends to be concentrated in several areas, which gradually change position. The ice mass from the base of Sherman Peak over to Pooch Peak has been undercut by extensive melting in recent years. It is difficult to monitor individual fumaroles on an annual basis because surface rock and soil are so unstable, but scientists have been able to observe overall patterns of activity. In late summer of 1976, a group from the Eastern Washington University Department of Geology came here to continue monitoring conditions in Sherman Crater. Dr. Eugene Kiever is assembling a measuring instrument here, assisted by Dr. Felix Muchler. One way to monitor the fumaroles is to periodically measure the velocity of gases escaping at various points. Dr. Kiever is using a pedostatic tube to check this. A pressure change caused by gases rushing past a tube with tiny holes in it displaces the alcohol in a manometer, stoically held by grad student Roger Hughes through hot, sulfury gusts. The velocity readings are correlated with temperatures and measurements of the size of the fumarole openings. It would be hard to obtain a precise assessment of the total heat output of all the fumaroles in the crater. Just getting to them is often quite a project. But these measurements provide at least some indication of the general pattern of activity. Though they can perhaps draw limited conclusions from the data they gather here, the time element and the enormity of their subject make it hard for researchers to predict what the ultimate usefulness or impact of these studies might be. Much geological fieldwork has to be approached in this somewhat speculative way, with the presumption that once information is made available, it will provide further glimpses of Earth processes which can never be observed directly. Some of Dr. Muchler's work illustrates how such information can be used. He and his associates have compiled a computer index of data about the chemistry of rock samples collected along margins of the vast sections of the Earth's crust called plates. The Cascade volcanoes, including Mount Baker, have emerged along a trench system where two plates are moving toward each other. The volcanoes in the southern Pacific are rising along a ridge crest where plates are forming and pushing away from each other. Thousands of rock samples have been gathered from volcanoes along these margins, then subjected to chemical analysis, which has been reported in journals of petrology and similar publications. To interpret the meaning of this expanding collection of data, Dr. Muchler turned to Eastern's computer services. Working with program analyst David Barr, Dr. Muchler and others have processed and stored this information on punched cards and magnetic tapes and disks. Here they are revising some of their entries. The figures on each page of printout are displayed on a screen, and Dave changes specific lines through an electronic keyboard. An important characteristic revealed by computer analysis is that volcanic rocks formed where plates are pushing together tend to be mostly of a type called andesite. Those formed where plates are moving apart are mostly basalts. Andesites and basalts are distinguished mainly by the amount of silica in them. If this relationship between rock chemistry and plate movement is consistent worldwide, then small samples can provide a dynamic record of changes in the Earth's crust. The information processed by computers here at Eastern was obtained from reports in scientific journals from individual researchers all over the world who probably had no direct knowledge of how the data they gathered might be used. Though this is not unusual, it illustrates the importance in geology of extensive gathering and sharing of information. A sample might represent a tiny speck of the material present in a given area, yet the relationship between its chemistry and location can provide knowledge about the movement of entire continents. Sherman Crater functions as a collecting basin for 50 to 60-foot annual accumulations of snow. The weight of successive layers compresses the snow into a mass of ice which covers most of the crater floor. Warm gases and steam from fumaroles beneath have melted cave passages out of the ice. Dr. Keever and Jack Snavely, a science teacher and expert mountaineer, clamber down to the cave entrances along the northwest side of the crater. Mount Baker is one of the few volcanoes known to have produced a crater ice cave system. These formations have also been found on Mount Rainier and Mount Hood, and are of particular interest to Dr. Keever. He explores caves whenever he can, and first surveyed and mapped the ice caves on Mount Baker in 1974. On previous trips, high concentrations of carbon dioxide and hydrogen sulfide in the cave system made gas masks essential. But so much melting had occurred that the passages were quite large and well ventilated this time. The cave floors are heaped with muddy soil and rocky debris deposited by streams of meltwater which trickle through everywhere. Air currents occasionally fill the passages with clouds of steam, and water dribbles constantly off the glistening tunnels of ice. Dr. Keever found that even the deepest layers were not true glacial ice, which is much denser. The oldest accumulation of ice he has found was 15 annual layers. By comparison, ice found in Mount Rainier's crater is as much as 50 years old. This indicates a much more rapid rate of melting on Mount Baker. Dragging transits and measuring tapes through here is a stumbling, soggy chore. But surveying provides data from which Dr. Keever can estimate Mount Baker's heat output. He does this by correlating the size of the cave passages with the rate of melting. To determine the melt rate, Dr. Keever punches a small hole in the ice and records its depth and the time. He will return later and remeasure the depth of the hole to see how much ice has melted away. On this trip, it was disappearing at a rate of about a half-inch per day. Combining measurements of the cave passages, estimates of the volume of ice melted each year, and fumarole measurements, Dr. Keever arrives at an estimate of the total heat output, one of the most important indicators of volcanic activity. Surveying the surface topography of the crater ice seems to attract more volunteer help than work in the caves. Sherman Peak makes an excellent reference point, as Roger Hughes and Dr. William Steele here take careful readings on prominent reference points and record the azimuth and elevation. A thorough survey requires many such sightings and very accurate notes. When they return to their labs on Eastern's campus, the researchers meticulously scaled down and plot the data points they recorded. Relating changes in the surface topography to changes in the cave passages enables the geologists to discern the pattern of heat loss. Once they know the kinds of changes which alter the surface topography, they can fairly well estimate the level of geothermal activity which produced those changes. Descending from the west rim, the group headed toward caves which led to the huge lake pit, which formed after a sudden upsurge of heating during the winter of 1975. Referring again to the drawing of the crater, most of the cave entrances lie along the base of the west rim. To reach the lake pit, the group had to go in at the base of Pooch Peak. Access to the lake was much easier than on previous trips, when it required an unnerving trek through black, steamy passages starting on the far north side of the crater. A tremendous outflow of energy was needed to melt this opening in the crater ice. A thick sulfury residue yellowed the fumarole fields along the northeast. While Jean and Jack took temperature readings there, the others prepared to launch a rubber raft. A major component of the geology department's naval fleet, the raft had in the past floated through many river canyons under the name Maid of the Schist. Felix felt that the raft's new role here in the placid pit called for a new name, the Crater Queen. The rechristening was followed by the inflation ceremony, conducted almost exclusively by Felix. John Mutchler, who had hauled the raft up over the west rim and down to the lake pit, busied himself with the less rigorous task of rigging the thermometers they were going to use in the lake. A few drops of Van Rosé on the bow, and the raft was launched. Jean and John headed toward a churning underwater fumarole, hoping that the mineral content of the water wouldn't dissolve their craft. They took temperature readings at several points to see if there were significant variations from the edge to the deepest part. They found that the large fumarole in the center stirred the water enough to keep the temperature fairly constant everywhere. The consistent temperature would make this an ideal place to install a sensor which would allow continuous monitoring of the thermal activity, regardless of the weather. It is hard to imagine anything growing in an environment battered by North Pacific storms and highly polluted with sulfurous compounds. But Felix found grayish strands of sulfur-fixing bacteria thriving in a stagnant pool. Volcanism and freezing are thought to have been the basic processes which originally produced organic molecules on the Earth. Chemical constituents spewed out of volcanoes were frozen, concentrated, then organized into amino acids by the crystalline structure of ice. An opening of this size is rare in crater ice formations, and because it formed so rapidly, it was possible to observe the entire process and document it for comparisons with volcanic activity elsewhere. From Grant Peak, the overall effect of the Lake Pit fumarole activity is clearly visible along the base of Sherman Peak. Researchers from Eastern Washington University are not the only ones involved in studies of Mount Baker. This is Dr. Stephen Malone, a geophysicist from the University of Washington in Seattle. Dr. Malone has directed seismic monitoring of the volcano since 1972. He makes frequent trips to Sherman Crater and has installed seismic stations and other instruments at several points there and on the flanks of the mountain. He monitors Mount Baker's seismic activity because it can indicate temperature changes inside the volcano which cause the rocks to expand and crack. It can also reveal the movement of fluids or the effects of the pressure of the volcano's mass on the Earth's crust. Eruptions are almost always preceded by earthquakes. Dr. Malone is currently operating 4 seismic stations on Mount Baker. Installing or removing the sensors is no minor project. Even though the surface soil here was quite loose and unstable, it was solidly frozen just below. Certain aspects of geophysics fieldwork are thought to build character, preferably among grad students. The lucky grad student here is Dave Frank, who was studying under Dr. Malone and working for the Geographic Survey. He was collecting small samples along the south rim of the crater, working his way up toward Sherman Peak. If you look carefully where Dave is scraping, you can see dark soil covered by a thin layer of light-colored ash, which was blown out during an eruption long ago and deposited here. Dave places the samples in small containers and carefully notes where they were gathered. These are later cross-analyzed with samples from other areas. From this, he is attempting to develop a more detailed picture of recent eruptive activity and of the movement of mud flows and avalanches. The approach is similar to Dr. Muchler's studies, only the sampling is being done in a much smaller area. At least here, the drudgery of collecting samples is relieved by breathtaking views of the Puget Sound Basin. It was not so breathtaking back in the crater's pungent fumarole fields. Both Dr. Keever and Dr. Malone periodically checked the fumarolic activity at various locations, but their observations are limited mostly to spring and summer. At other times of the year, when the weather all but prevents access, they depend on seismic sensors to signal changes. The sensors Dr. Malone has installed are connected to this equipment, which transmits impulses back to the laboratories where they can be recorded. Some of this information is beamed directly down across the Cascades to the University of Washington. The rest goes to a power company maintenance area near Baker Lake. There, a mobile receiver is set up. Equipment inside a trailer records the radio signals on tape. They can also be transmitted to the university by phone lines. Home base for this operation is considerably more elegant. This is the Geophysics Building on the University of Washington campus in Seattle. Here, Dr. Malone has offices, labs, and maintenance facilities. An extensive seismic monitoring network has been set up. Compared to Mount Rainier or Mount St. Helens, Mount Baker has been a disappointment to seismologists. In 4 years of monitoring Mount Baker, only one locatable quake has been recorded, that is, one detectable on more than one sensor. Several locatable quakes per year show up on Rainier and St. Helens, along with dozens of tremors which are detected on only one sensor. For recording these tremors, Dr. Malone uses a seismograph. It has a strip of paper attached to a drum that's set to revolve at a specific rate, generally once per quarter hour. The data from one day's observations from one seismic station is recorded per sheet. The small deflections you see here are mostly due to the shifting of glacial ice. This type of monitoring recording setup allows scientists to monitor seismic activity as it occurs. In addition to the seismographs, Dr. Malone uses equipment which stores information on film and computer tape. These, called developcorders, record impulses photographically on a strip of film. The film is continuously processed by the machine, and the recordings can be viewed on a screen 11 minutes after detection. Impulses from a network of sensors are recorded simultaneously. This makes it possible to determine the sequence in which a tremor was detected by the sensor network, and from that obtain a fix on its epicenter. In addition to seismic monitoring, Steve has set up a slope stability experiment on Lahar Lookout. Lahar Lookout is the rocky promontory on the right. Sherman Peak is on the left, and the Boulder Glacier extends down from this area, forming a natural chute. This is the floor of the East Gap at the base of Lahar Lookout. Heat and sulfur-laden steam from the large fumaroles here are undermining and weakening Lahar Lookout. The hydrothermal alteration turns the supporting rock to clay. Should a massive section of Lahar Lookout break loose, setting off a large rock avalanche, the debris would cascade down across the glacier, following this icy chute already streaked by small slides and ash from the fumaroles above. Friction from the massive rock would melt the ice and snow on the glacier's surface and produce a huge mud flow which would hurtle down the mountainside. If it reached the lower valley and pushed into Baker Lake, it could be disastrous. This is the track which many such mud flows have followed down the Boulder Glacier in the past. There are very similar structures in the Nooksack River drainage on the north side of Mount Baker. The worst possible catastrophe would occur if a large mud flow suddenly displaced so much of the water in Baker Lake that it overtopped the dam which forms it, unleashing a flooding wall of destruction down the valley. It should be emphasized, though, that the likelihood of anything so cataclysmic as all of this is very, very small. Whatever changes that do take place will probably be quite gradual and mainly of interest to scientists, but some precautions do seem justified. Impulses from the tilt sensors on Lahar Lookout are telemetered directly to the University of Washington labs and recorded continuously along with the seismic data. Since slight tilting is usually detected in soils before a landslide, this should provide an early warning. Even if no slide occurs, Dr. Malone is gathering useful background data on daily and seasonal changes. The tilt meters are so sensitive that even the slight changes from solar heating are detected. There is a constant flow of data in from the seismic station network. Computers are indispensable for processing and analyzing all of this information. And the one Steve is using here has some features which make it very well suited to geophysics. Basic materials such as maps or schematic diagrams can be stored and entered from magnetic tapes. A smooth whirling swivel chair is essential. Instructions and new information can be entered from a keyboard or from punched cards. The material Steve wishes to work with can be displayed on a television screen. But the most interesting feature of this setup is this plotting board. With it, information can be positioned by sound waves. The position of the coordinates, which appear on the TV screen, is determined by measurement of the time it takes for sound to travel from the small pointer Steve is using to two microphones positioned along the left and rear edges of the plotting board. As he works, he can check his entries on the screen. The system will generate a paper printout as well. But before elaborate data processing equipment can be put to use, information must be gathered in the field. Taking temperatures in the East Gap can be pretty hard on thermometers. Notice the thick deposits of sulfur crystals around the fumarole openings. Some samples were removed and taken to the geochemistry labs at Eastern to be analyzed. There are usually traces of other minerals along with the large amounts of sulfur in the samples. And if the researchers can find out which trace minerals are present and in what amounts, they can distinguish samples from Mount Baker's East Gap from those collected in other parts of the crater or on other mountains. One way geologists do this is with a technique called X-ray diffraction. The process seems to combine medieval alchemy and atomic science. Bill Steele is preparing a sample for analysis by pulverizing it into a fine powder, which he mixes with water. Mineral crystals are made up of layers of atoms. Each type has a characteristic amount of space between the layers. An X-ray beam going through a mineral sample will bend, much like water bends light beams. Each mineral in the sample will bend part of the X-ray to a characteristic angle, according to its atomic spacing. Bill positions a bit of the sulfury paste in the path of the X-ray beam, then switches open a port which allows the X-rays to stream through. A detector moves slowly around the sample, sensing the intensity of the X radiation at points along an arc. The angles and intensities are recorded on a strip chart. Monitoring the forces at work on Mount Baker requires samples and measurements which are subtle, indirect, and often amazingly small. They contrast remarkably with the volcano's size and the tremendous forces which it seems just barely able to contain. The only greater contrast is between the expanse of time over which these forces have operated and the comparative instant during which researchers are able to observe the result.